3D structural modeling session for the NCOSE and Structural Modeling Working Group project. We are started live now at 8 o'clock for our presentation by Kevin Dye, which is a natural history of interpretive structural modeling. And I will let Kevin introduce himself and continue with the discussion. Kevin, please take it away.
So, Joe, you're handing control over to me now?
It's yours. You should have it now, Kevin.
Okay. Good morning, everyone.
Maybe having.
This is on. I still need to set up the global meet. I will do it. Your audience assembling now.
Yeah, maybe have 2 or 3.
It's a little late.
Yeah. Give us a minute or two.
We are recording now at this time, so if you could can you mute your microphone while you're doing that so Kevin can keep going with the broadcast? Kevin,
Gary,
online.
Should I start?
Yeah, just go ahead. Can you mute NCOSE? Can you mute your microphone?
Yeah.
If they mute, we won't be able to hear them ask questions, though, right?
Come closer. We have a challenge with the global meet, so we have to do through the.
Well, if they don't mute their microphone, what happens is every time they talk, the video goes to them.
1 second. Mute the microphone. That mute button. Yeah. Yeah, we are muted.
Oh, good. We got it now. Thank you. Go ahead, Kevin.
Okay, good morning. Can everyone hear me?
I can hear you.
Can people in the room hear me?
So we don't limit it, but
Uh,
at the same time.
Hello. We have a session here.
Okay, I just is that what you're
No,
trying
no,
to say?
please join us.
Yes, the answer
Please
is
join us and we have a challenge with regards.
Are we ready?
I'm
Okay.
ready, Kevin.
Okay, so good morning. My name's Kevin. I'm the Director of Research for the Institute for 21st Century Agoras, which is a nonprofit that is the caretaker of the methodology of what...
Okay, we need to get started. Have a seat. So we get started.
The Institute is the caretaker of the methodology.
He already started. He always started the Hangout, but I have a problem with the global meet. Because
Okay, so have a seat. We've got a 3-hour program this morning, and this is on Joe Simpson has a group doing structural modeling. So he has between now and the coffee break at 10. First hour is structural modeling history, Kevin Dye. Second hour, current structural modeling approach, Joe Simpson.
You want this muted?
Yeah.
When you're talking about that.
Okay.
And then we go coffee break, come back at 10:30, 11:30. Third hour is the future of structural modeling, and that'll be an open discussion. Like, once you've heard what it's all about, where do we want to take it? Where would we find some areas of application? What would we find it useful for? I think it would be great to get some other working groups to start using what they're coming up with. So I think that there may be some people here from the model-based SE area, so they can kind of help us, since he's coming up with basically a new modeling approach In fact, he's developing his own modeling tool, which you'll hear. It's something that will be foreign to a lot of people, but it's a way to truly implement some system science principles in the systems arena. So I look forward to this. You think we're technically ready yet?
We're ready on this end. Kevin's ready to go.
Okay. So are we?
No, I just have to
ready?
start the recording now. I'm there almost. I just have to record this. Okay.
And 11:30, Sue will kick us off on her talk. And she's going to continue after lunch until 2:30. She's going to be talking about agency and causal factors in social systems. Okay, so that's a modeling topic also. Okay. You've heard of agent-based modeling, so I think you have some interesting things there. Okay. We are ready to go.
1 second. It's not allowing me. Only web only, so I'm not able to record this web and audio.
We're ready to go here.
I would not worry. Okay, you're going to.
Joe's recording.
Okay.
That means you won't get the audio.
It's all being recorded.
Okay, now Joe Simpson is recording it on his side, so we'll make the full recording available because we're trying to get Global Meet and Google Hangout to work together, and they don't. So the Google Hangout will be a full recording, you know.
And we'll put that goes automatically onto YouTube.
Yeah, so he'll post it on YouTube. We'll send out the link to everybody afterwards. So we ready to go?
1 second.
Okay. Val?
No sharing. Where is it?
It looks like there's only one person dialed in
Okay.
for Global Meet anyway. Sorry about that.
Okay, are we ready?
Yeah.
Okay, go for it, Kevin.
Okay, hi. I'm Kevin Dye. I work for the Institute for 21st Century Agoras on research to be a caretaker for the methodology now called Structured Dialogic Design, previously called the Cognoscope, previously called Interactive Management, previously called Interpretive Structural Modeling. Now interpretive structural modeling is considered one of the methods of the overall methodology. I do consulting work for Dialogic Design International. For the last 3 years, my primary client for that has been the Air Force Research Labs. And then I help work with the Future World Center, which is a nonprofit dedicated to peace building between the Turkish and Greek Cypriots as one of their many charges, and that's in Nicosia. So I'm going to give a brief example of structural modeling and a description. Then we'll go through some history, and this is kind of the intellectual heritage. During that, I'll take the opportunity to cover some key technical aspects that would be of interest to systems engineers. Then I'll discuss an overview of applications, software implementations, and the publication trends. I'll have a couple slides of reflections, and then we'll have a Q&A. So, interpretive structural modeling was announced at a systems engineering conference in Purdue in 1972 by John Warfield. John Warfield was one of the first authors of a book on systems engineering back in 1956. And Warfield's a major player on implementing structural modeling. The structure is the topology or the graph or the sets, independent of what the elements and the relations on them mean. We won't get too much into that, but it's been part of a long trend to get there, as you'll see. Sometimes said that Gauss was the first to recognize this trend towards pure structure, and one of the aspects of going to that structure is it helps us implement von Bertalanffy's idea of isomorphisms, because once you identify the mathematics of the structures, the premise is that findings of structures may be applicable from one domain of application to another. This is one of the more recent applications I did with the Air Force Research Labs. It's on the future integration of cyber and electronic warfare, and as you can see, most of the content has been redacted so that I can present it. But the active redaction actually surfaces the idea of the structure. And here we have two structures, one in pink, which are challenges in the synthesis or integration of these two realms of the research labs, and the blue are the solutions. Each of them have their own structure on their own, and then there's a cross impact between the solutions and the challenges. This was published in the Journal of Technological Forecasting and Social Change. Most of the early work on interpretive structural modeling was published in the Transact Systems Man and Cybernetics. So what is structural modeling? It's an elicitation technique which has a formal language for representing knowledge in terms of the structure, which can be represented in multiple ways. One way is as directed acyclic graphs, which is an example that I just showed you. It also can be represented as partially ordered sets and relations amongst them. That's often useful for deriving new theorems about structural modeling and developing new algorithms. It also is representable in binary matrices or Boolean matrices. With Boolean algebra, this is often the representation that makes it easiest for computer software to do the calculations. It has an abductive logic inference engine. It's not that fancy. It's primarily using the rule of transitivity to infer how to fill in the matrices. There's an advantage to it because it forces you to consider connections between things that might be far apart, and it also infers connections between things that might be far apart in the diagrams. And so there's a quality enhancement aspect to it, and then because there's inferencing going on, it speeds up the model creation by about 75 to 80% compared to filling in a matrix without any assistance. And the interesting thing about the ISM algorithms that Warfield created is as the matrix gets larger, the time savings as a percentage goes up. And this is very unusual. So it's a scalable technique. And it's considered a front-end technique, so it's sometimes lumped in with so-called problem formulation methods. There are other types of structural modeling which basically give you a matrix to fill in and don't give you any ways to save time in doing it. So that's a key distinction of interpretive structural modeling versus other types of structure modeling, which are basically different ways of analyzing an already existing matrix. And so the big breakthrough that happened with a guy named Frank Harari, who is one of the forefathers of graph theory, and he combined Boolean logic with the notion of inference on the logic, which goes back to all the way to Aristotle and syllogisms. The idea of transitivity was articulated by Pierre Abelard in medieval times, and finally started to be dealt with in terms of inference by Charles Saunders Peirce around the turn of the 20th century. And Harari recognize that the diagrams or directed acyclic graphs could also be represented by Boolean matrices. Excuse me. And it's this fluidity of moving between different representations which gives interpretive structural modeling its power. So there's going to be a few slides on how this is done. This overall method, while it can be used by individuals, and there's a lot of publications of individuals using it, in the branch of applications that came out of John Warfield and Alecko Christakis, it's built for doing large group, small to large group meetings, usually not less than 8 people, usually not more than 80 people, but there have been applications done with hundreds of people. There's a decision seminar room, which comes from the inspiration of Harold Laswell, who's the person that coined the term policy sciences. He was a communication theorist, and Warfield became kind of his implementer. And so you see what looks like a war room. The walls are, by the end of a session, are typically covered with displays. What you see in the upper left are clusters. And you'll also see the structure such as I produced on another part of the wall. Now, these are the steps that are gone through in one version of using interpretive structural modeling, which happens down there in the middle of the bottom rung. So there's typically an elicitation of ideas, which is often done with nominal group technique, an upgrade to brainstorming. There's a focus on a particular question, which is kind of linguistically engineered between a broker of the group and the facilitators. Their ideas are elicited. They have a couple rounds of clarifying the meaning, especially by drawing distinction between ideas. And they go through a clustering activity to inductively develop a sense of how ideas are alike to each other. During the course of this, they tend to develop a set of assumptions about what they're modeling, and they also often coin or adopt language specific to the situation. There's a round of voting, and nothing is done with the voting except to show what they learn after they go through the structuring. And what they often learn is that what they thought was important is not what they determined to be influential after they go through the structuring. And then whatever structure we're working on, there's then we often do a cross-impact map to a previously developed structure. So for example, prior to an event, we may do interviews and a literature review and develop an understanding of problems. When we get to working with the group on site, we'll develop a structure of the challenges and addressing those problems, and then we may do a cross-impact map of those two. And then we repeat this process again for the solutions, and then the solutions will get cross-mapped to the challenges, and so forth. This is me in the lower right, and I learned this from this methodology from Alecko Christakis, whom I met 2 years before I met him face-to-face through his literature. I was working for United Technologies, and we engaged the largest advanced technology program that the National Institute of Standards and Technology had run, and it was a consortium of 12 companies. It was called Rapid Response Manufacturing. At the core of it was the National Center for Manufacturing Sciences, and then about half a dozen software vendors. And we had Ford Motor Company, General Motors, Oak Ridge National Labs, United Technologies, Texas Instruments, several other companies that were all trying to unify computer-aided design and computer-aided manufacturing systems from concept to cutting apart. And there were four teams working in parallel, and the team at Ford, who led a group that included all the other companies, leapt ahead of all the other groups and accomplished in 2 weeks what the other groups took a year to do, which was the long-term 5-year plan for the project. And I said, I have to learn about this. So I started reading about the publications of Warfield and Christakis. And so after the solutions are developed, this is an example of one we did on the future of energy efficiency for the Pacific Northwest, and it was a 20-year horizon. And the applications that are typically been pursued here try to be as global as possible, as interdisciplinary, and long run as possible. Part of that is owing to Christakis' background in technology forecasting as one of his areas, and also Warfield's background in using systems engineering to manage complexity of large-scale projects. This particular view is overlapping the clusters of things that are similar, which are highlighted by the colors on top of the structure. Now, this is an example of two structures superimposed. So there's a clustering or similarity structure, and there's also a causal or influence structure on the same diagram. And research shows that people typically can follow about 4 types of relationships between things, and we see that in diagramming notations such as UML or Structured Analysis and Design Technique, IDEF. There's one or several types of relationships mapped at a time. But in the work that we do in large groups, we do one type of relation at a time generally. Now, one of the things I discovered in looking at this work is tends to be no relationship between what people vote on as important, which you see here in the orange, and what's found to be influential, which we're calculating as the amount of leverage any idea has on another idea. This became known as the erroneous priorities law. This shows you what's happening is in this structure at the top, the idea cluster that accumulated the most votes, you see down in the lower right in the red, really was not considered very influential. The most influential one, over here on the left of the structure, had one of the lowest number of votes of any idea. This discrepancy is very surprising. We think it's a good measure of organizational learning that is enabled by this methodology. So that's an example and a little description. We're going to move now to some history and intellectual heritage. The first is that the specific work that Warfield did on structural modeling, he attempted to build up into a science of generic design. Now, in 1987, or just before that year, the National Science Foundation set up a new directorate called the Design Theory and Methodology Directorate. And they commissioned Warfield and Christakis to develop a proposal of a science of design. And this was the model that Warfield and Christakis came up with, and it was largely inspired by the American pragmatist Charles Sanders Peirce. The idea that theory is not enough, but you have to feed back applications into the theory. That's a simple idea, but for example, in the realm that Christakis came out of, which was theoretical physics only occasionally worries about the results of applications and actual measurement. And this is also the case in the social sciences. And so it was only, back when they did this, it was only a few decades into the notion of action research, that the only way to know about a system is to try to change it and feed some back. That is a quote from Kurt Lewin, one of the founder of action research, and this was Warfield's attempt to get into that. Now, if we look at the around that time, this is a map from the early 90s that came out of Carnegie Mellon. They tried to look at all of the major design theories and position each of them within a taxonomy. It's a little difficult to do, but you see in the middle here, between the social and systems approaches, or between descriptive and prescriptive, sits Warfield, and he's the only one that spans the descriptive and prescriptive approaches in their opinion in terms of design theory. A couple other things you might find of interest under the prescriptives is a quality function deployment. Paul and Beitz, the major theorist on modularity in the early 20th century. Axiomatic design over here on the right, which is procedural methods. So this methodology got going through the confluence of interest between Hassan Özbakan, who is one of the premier theorists of planning back in the 1960s, John Warfield, and Aleko Christakis. They were kind of a three-person team. A man by the name of Aurelio Pache, who was one of the founders of the International Institute for Applied Systems Analysis, helped launch something called the Club of Rome. And they commissioned Özbakan to develop a proposal called the Predicament of Mankind, and that proposal was going to be funded through the Club of Rome and the Volkswagen Foundation and a number of foundational contributors. And a parallel proposal was made by Jay Forrester, the founder of Systems Dynamics from MIT, and he ended up winning the proposal and worked on doing a quantitative world map, a world systems diagram, and this became known as the limits to growth model. The work that Özbakan and the others did was on the front end, which is about 6 methods that were intended to front end the development of systems dynamics models, and they called it at the time the problematique. And these three were very bitter about that split, and so grew to hate Jay Forrester and the whole systems dynamics community. And that split has really been deleterious to the value of structural modeling and interpretive structural modeling being appreciated in the systems engineering community. And it was very much a personality thing, and it's something we need to put to rest. Now, Aleko Christakis, which came into the fold here, was a theoretical physics. His mentor at Princeton as an undergrad was John Archibald Wheeler. He's the guy who invented the term black holes. And two very interesting philosophies that he imparted to Christakis. One was it from bit, that in a way everything down to the quantum level is created as a result of information. And the participatory anthropic principle is that people, in a way, create the universe. They create the things they look at by looking at them. This is kind of a strange idea, not well accepted, but it was very influential in Christakis' view of the role of the observer. And the role of the observer he was responding to was Heisenberg's uncertainty principle, that the act of observation can change the observation. And Christakis' work at Princeton had to do with reworking Einstein's general theory of relativity differential equations. You see Einstein there walking across from Wheeler. And to work on those differential equations, you engage field theory, of course. Now, after Christakis was working in theoretical physics, he needed more work. He was working in Greece at the time for the army. When he got out of the army, he went to work for this fellow named Doxiadis, who was kind of a futurist and a town planner, and he was working on projects that were larger than had ever been attempted before. For example, a megalopolis that would be all the way from Boston to Washington. And what happens if we have a city where Route 95 is Main Street and it's a 1,000-mile size city, a mega city? And so Doxiadis commissioned Christakis to develop a language and a theory for human settlement to be based on field theory, but also to have the language of urban planning and architecture. Christakis eventually gave up on the idea. He thought it was too difficult, but that what he did learn from it is that the value of engaging people that are involved in the effects of the planning rather than just the planners. And that's what he took from that. Now, the other player here, John Warfield, was primarily an implementer of structural modeling not so much invented as synthesized by Frank Harari. So Frank Harari is a mathematician and often credited with doing one of the first books in English on graph theory and what he called structural modeling. John Warfield was, I would say, a great appreciator of that and really implemented the applied software that took advantage of that. And the thing that drove both of them was an interest in the value of a constructed language and the ability of a language to simplify notations. We're about halfway through. Does anyone have any questions? No?
No.
Okay, so here's some progenitors of structural modeling as synthesized by Harari. One's the theory of relations developed by De Morgan. Graph theory, one of the early progenitors of that was Euler. Set theory of the Russell and Whitehead program, and also Frigg. Binary matrices, whom Cayley is often cited for. Boolean algebra, George Boole. The idea of formal languages, that you need to develop languages specific to the domain of inquiry, Frigg and Hilbert. The idea of hierarchies, which really got going in the systems movement in the 50s, Herbert Simon and Mezirovich. Abductive inference, one of the early influence of that was Whewell and then Charles Sanders Peirce. And then someone who kind of came out of left field here really showed the value of structural modeling when you're modeling whole organizations, and that was doing quality function deployment, often attributed to Akao at the Mitsubishi Kobe shipyards in Japan, and then Don Clausing, who popularized this as the House of Quality in a famous Harvard Business Review article he did with John Hauser from MIT. And just as an aside, Warfield, when he was working for Battelle Memorial Institute, had a contract to introduce techniques like that led to interpretive structural modeling. At the time, they were just working at the matrix level without all the other representational horsepower or software, and that was called unified program planning. That got introduced to Mitsubishi. Then a decade later, publications started coming out called Quality Function Deployment, which is a mistranslation of unified program planning. This is another software of Warfield over the years. So where did this come from? Aristotle is attributed with the early notion of syllogism, and various books made it into the medieval period at different rates. But Pierre Abelard is really identified as the first to articulate one of the rules of syllogism, which is the idea of transitivity. At that time, there was not that much of a difference between reasoning about logic and math and language. It was all kind of jumbled up. These were not distinct fields. And for example, Boethius was very interested in music, and identifying the structure of music was very similar to dealing with syllogisms to him. Both Abelard and Boethius were very interested in poetry and writing. So the mix of language with math and logic was all a jumble in the early days. Now, two intellectual breakthroughs that happened was Pierre Abelard got rid of the idea that the meaning of a syllogism, the entailment of a syllogism, had anything to do with the nature of the things that it connects. This is a revolt against Aristotle, who really included what the particular items were in a relationship as part of the meaning. And Occam severed the connection between relations and the items that represented the relations. So between these two, in the medieval period, they really got to the idea, some of the early ideas that would give us the notion of pure structure later on. Now, another branch that led to graph theory was the confluence of logic, algebra, relations, and sets. These were all independent realms of investigation back in the Enlightenment period and into the early 20th century. But a key figure here is Auguste de Morgan, and he's famous in logic for having a rule named after him, De Morgan's rule. But he really developed the theory of relations, which formed the basis for set theory and Russell and Whitehead's famous Principia Mathematica. And it was Kuratowski who came to recognize that the theory of relations and set theory were really the same thing, and that they could be used interchangeably. Excuse me. And of course, it was De Morgan that inspired George Boole and the development of Boolean algebra, and his association with Babbage and so forth, which is kind of his story. Now, the birth of the matrix is fairly complicated, but it started with, again, in the realm of language and what was referred to as rhetorical algebra. There were rules for reasoning about simultaneous equations, but there were rules about using language. And although they wrote things in the form of a matrix, they didn't have the ideas of coefficients or matrices at the time. And this kind of carries through to the point of 1850 when a guy named Sylvester invented the term matrix, which means pregnant animal, which I didn't know. It's from the Old French, means it's a pregnant animal, and Sylvester used that term because he viewed a matrix as being pregnant with determinants and ready to give birth. In Latin, it means the womb. And he had a strong relationship with Cayley, who is often cited as developing the early notions of matrices. So this is an example from 200 BC of the posing of a problem and how it came to be represented in the first matrices. And then the rules of rhetoric were about using language to solve it. But there's a clear line from De Morgan to Sylvester to Cayley. Sylvester also coined the term graph to describe what became known as directed acyclic graphs. And Sylvester was also a person very interested in poetry and wrote a whole book that was considered a disaster, but it attempted to analyze the rules of language use in poetry. And he was just as interested in that as he was in math. But here's the guy, a key guy, who, owing also to his language use, coined both matrix and graph that we still use. So there's a couple technical aspects I'll cover. One I mentioned, unified program planning. Here it is cited by Sage in one of the classic textbooks on systems engineering. and this is by Hill and Warfield. And their idea was there would be a cascade of matrices that went across all the different phases of system development. And so the self-interaction matrices, or the adjacency matrices, are here along on this diagonal, and they're just showing the upper triangular. And then the cross impact from one to the next is shown in the rest of this. And so you can get the idea that these things get very large scale. And there's very few publications about this. And one of the reasons is it was used on very large scale projects in defense and aerospace, and they had no interest in publishing it. So this is an aspect that kind of got lost. But as I mentioned, it's a technique that got introduced to the Japanese and resurfaced as quality function deployment years later. Unfortunately, they missed the advancements of interpretive structural modeling, which would help them fill out those matrices. Now this is a kind of a small size graph, but it shows you another branch of structural modeling done by Don Stewart. He called his work Design Structure Matrix, Dependency Structure Matrix, and this is another branch of structural modeling that works from after you get the matrix filled in, what can you do with it later? So you can do things using Warfield's algorithms for understanding the hierarchy and drawing the digraphs, and then tiering the equations so that you can develop modularity and get rid of change propagation, so you can have parallel project or software or systems development going on. And there hasn't been many people that are in Don Stewart's camp of design structure matrices referred to early papers by Warfield about how to process a matrix once it exists, but they very rarely use interpretive structural modeling to fill in the matrix. Now there's starting to be that, especially at MIT and in India. They're starting to marry the two. But this is an academic encampment. These guys just didn't talk to each other very much. And they had their own little niche to carve out in the world of journals. Now, what does partitioning mean? So here's the idea, an initial set of interactions between requirements, and then sorting it into block triangular, we're able to identify a module that if you change A, C will have to change. If you change C, A will have to change. And that's something you would want to modularize and prevent from propagating across the whole system. And so you'd condense that into a single module, as you see in step 3, and you end up with what's referred to as the lower triangular matrix form. And then anything that shows up in the upper right is kind of a danger signal for systems design, because it means that you're going to have change propagation across the system if there's an update. And then you can recognize patterns in this. There hasn't been as much work on automated pattern recognition, but this is an example of a layered system where A and C depends on things in B, but not the other way around. So it's a nice layer, and D depends on A and C. So that's a 3-layer architecture. So this is the most commonly cited article from Warfield across all the different structural modeling people. Here on the left-hand side, you see the adjacency matrix when it's initially filled in, then the rearrangement through tiering and partitioning into modules, and then the directed acyclic graph that results. And here's an example of, from the previous example of how these get larger and larger. Now, in the case of quality function deployment, Ford Motor Company, as an example, was using quality function deployment in the 80s. They're trying to catch up to the Japanese. And they found that the matrix for a car door alone was a 300 by 300 matrix. And it took a team of 6 people several months to fill it in. So they were very interested when they heard about interpretive structural modeling, and they became Warfield's largest funder. And so you can imagine if you're doing a car door and it's a 300 by 300 matrix, what happens when you propagate that across the relationship of the door to all the other systems it interacts with. So they were very interested in in reducing the amount of time that it would take to fill these things in. And Xerox and Hewlett-Packard had similar problems with the scalability of quality functional deployment. This is an example of use in a weapons system analysis at MIT, and you see the cascade of matrices like I showed you, and how big these systems build up. Now, excuse me. By the 1980s, there was over 100 different types of algorithms that referred to themselves as structural modeling. And interpretive structural modeling is just one little item up here by 1B. That's one of many different types of structural modeling. This was viewed by George Lindaris. He kind of had a view of it. And this branch, the people that paid attention to all the things you could do with the matrix after you had it, excuse me, were largely in the realm of multi-criteria decision-making. And the literature in multi-criteria decision-making does not reference the people that are typically doing product development like George Stewart, like Stewart's dependency matrices, and vice versa. The people doing product development and systems development don't typically reference any of the literature on multi-criteria decision-making structural modeling. And this is something that has to change too. Now, the thing that really distinguishes interpretive structural modeling from other things that are called structural modeling is the inference that happens ahead of time. And this is done by the law of transitivity, which we understand if A influences B and B influences C, we can infer A influences C. We don't have to ask about that. When you're doing that in a matrix of the 13 areas in the matrix, you can fill in about 8 sections of a matrix every time you get a new answer, and then you can look for the area of the matrix that you have the least amount of information and ask the question there. Now, this idea of being able to do inference across transitivity is largely attributed to the founder of American pragmatism, Charles Sanders Peirce, who also came up with the idea of semiotics. And Peirce was also really the inspiration of John Sowa, the inventor of conceptual graphs, who's often cited as the father of the semantic web. Sanders got his idea on abduction from William Whewell, who coined the idea of induction, and he was interested in processes of discovery and how logic might be applied to process of discovery in order to try to speed them up. Whewell happened to also coin the term science. He also coined the term physicist. So he's a very intellectual heritage. And Whewell's inspiration for ideas on scientific discovery were largely inspired by Francis Bacon. One more piece to get to graph theory of Harari, and that was Euler solving the problem of the Königsberg bridges. And this was a folk problem. There's a city in Prussia where there are 7 bridges and 4 land masses. And the question was, can you cross every bridge just once and end up at the same place? And this problem went unsolved for many years until Euler addressed it. And his big breakthrough was to solve the problem with symbols that represented the graph instead of trying to draw them. Because if you try to draw all the possible combinations, there's too many combinations. He was able to identify a relation as a set of its vertices, AD, AC, AB, were different bridges that you could cross. And through reasoning, kind of linguistic and logical reasoning, using the symbols, he was able to solve the problems of graphs and kind of gave birth to graph theory. So this was all brought together by Frank Harari. Frank Harari collaborated with Doran Cartwright, who was a social psychologist that had been hired by Kurt Lewin. Kurt Lewin was inspired in his development of social psychology by Max Wertheimer and Ernst Cassirer, who kind of philosophers of the theory of psychology in Germany. and they were friends with Einstein. Wertheimer had the idea of Gestalt psychology, that you can't understand a person based on trying to type them, like saying they're a happy person, therefore they behave in a certain way. He believed you had to look at the whole picture of the relationships they were involved with. And this is very similar to Einstein's notion of field space, the totality of all the coexisting facts which are conceived of as mutually independent. This gave birth to field theory, which on the previous slide you saw influenced Wheeler and Christakis in his work, but it became the metaphor for a new type of social psychology called field theory that Lewin was inspired by. And it was Lewin's drive to develop a fundamentally new theory of psychology to move from Aristotelian categories of people and their psychology to causative aspects in the field of interrelationships in their environment that drove Darwin Cartwright to collaborate and hire Frank Harari, the mathematician, to develop these tools. And Harari recognized that Boolean algebra, matrix algebra, graph theory, all could be combined. And although there was a book on graph theory published in the 30s in Germany, it didn't make it into the English for quite a while. And Harari's often cited as one of the founders. Warfield tried to keep track of his intellectual influences in the development of things, and he has a number of publications like the one here, where he identifies people at the intersection of how did they make a contribution to his thought and which area it was. But he was a little sloppy about his different articulations about this. So that's a technical aspect, so I'm briefly going to go over some applications and reflections. When ISM, the software, was introduced, it went out to a number of typically large government agencies and tested. This is one list of them, but it's a fairly large list. And to the fairly early on, they went into Japan, South America, and into Asia and China. That was in the first decade of them working. And the applications they could do is structures where the relationship is transitive and asymmetric and irreflexive. And there's about 60 types of structural relationships. And if you combine several of these, you can do models like UML or SML, or structured analysis and design technique, object-oriented programming, by combining different structures of here.
Kevin.
Yeah.
So could you do about a 3-minute summary and wrap up of where you are now, or close to your, and then we'll change and start the next session in about 5 or 10 minutes?
Yeah.
Thank you.
Yeah. So as soon as Warfield developed the algorithm, there was a spate of implementations around the world, and that's one of the problems that we're trying to solve now with the basic structural modeling, because there's been a lack of standardization across all these different techniques. One of the people working on software now is in Cyprus. Software and the methodology was introduced as part of conflict resolution in Cyprus, and after training 36 facilitators, they went out to about 2,000 people in a matter of months, and they're now one of the largest sites for the practice of this face-to-face methodology using interpretive structural modeling. And if recently we're bringing them into the fold of structural modeling. The current trend, the peak of English publications in interpretive structural modeling was 1980, but at that time there started to be a lot of publications in Japanese and Hindi and Chinese, and those are not represented here. Now, even in English, we're on an upsurge as of 2008. And then since 2009, there's been a tenfold increase in the number of publications on interpretive structural modeling as identified by Science Direct or Google Scholar. But one of the problems with this is people, after they come up with their own implementation of the algorithm, if they add their own name to it, it becomes difficult to track. So already after 80, the bulk of the publication rate shifted to Asia, India, Japan, China, primarily, and we have little access to that. It's another one of the aspects that we're trying to address. Of course, the math is something that we can share, and that should be one of the promises of the structural modeling effort. So this is an example of the problems. This is just a subset of all the different names that are used to mean basically the same thing for structural modeling. And every time I think this is largely because of the desire for originality and publishing. Every time something gets published, people want to put their own name on it. So, two slides of reflections.
Kevin, we can. You don't need to run through this. We can just start. You can just continue on on the next video. So this might be a good place to just take a little break, set up the next one, and ask if there's any questions, and then we can move on from there. How about that?
Sure. We can pause, and then we have 2 slides of reflections.
Yeah. So basically, we have. What we do is stop the Google Hangout recording now, then start a new Google Hangout. So it'll take about 5 minutes. Give people to think about this, and you can either answer questions, or we'll talk about the reflections and go through there. Is that okay?
Yeah, sounds good. I'll be here.
Okay, thank you very much, Kevin. This is very interesting to me. I really appreciate the work you put into this. I'm going to stop the Google recording right now and then set up a new one, and so we'll convene again in about 5 minutes.
Okay.